I wanted to take a minute and talk more about linearization because this seemed to be something people were struggling with as we investigated the internal resistance of a battery. So just kind of to set the context, we use Kirchhoff's loop rule starting in this location. If I go around the circuit, I get a voltage drop from the internal resistance of the battery. I get the EMF of the battery that's positive. It's putting energy into the system. I get another voltage drop across the real resistor, and then I'm back to where I started. So since in a loop you have no net change in voltage and you come back to where you start, that's my Kirchhoff's law equation. And if we were to measure voltage, we saw in class that the more current there was, we would see the measured voltage across the battery seemed to decrease. And this equation really shows why. So in terms of what I want you guys to do with this data, we're going to do something called linearization. And linearization is a way of checking two things. First, it enables you to find things you might not know. In this lab, the thing we're going to be looking at is the unknown internal resistance of this battery. The second thing it lets you do is it lets you check your model. So every equation we study in physics comes from a few basic ideas. Conservation of energy, which is really what Kirchhoff's loop rule is, but we sometimes see it as EO equals EF. Sigma F equals MA, net forces. And once you make an equation and it's based on one of these models, it's useful to see if you were correct in that model. So if you make a graph of lots of different values for the variables in your equation, you can check to see if your model's right. And the easiest way to do this is linearization. So we're going to try to linearize our model. In this lab, the variables I gave you an independent variable of resistance. We're going to change how much resistance there is in the circuit, and that's going to affect the current flowing through the circuit. So current is our dependent variable, and resistance, whatever resistor this is our independent. So the first thing you do is basically get those on opposite sides. Since a linearized equation is going to be like this, and we usually put the dependent on the y-axis, I like to get the dependent by itself, and then everything else goes to the other side. So let's try to isolate I. So 0 is E minus IR minus I big R. So E is I little r plus I big R. And I'm going to divide through by I. So I have EMF over I is little r plus big R. And now I'm going to basically divide through by EMF. So I'm left with 1 over I is big R over EMF plus little r over EMF. Okay, so now I've got my independent variable where y ought to be, and everything else is on the other side. I'm trying to make this equation fit this equation a little better. So I'm going to factor r out of this so I can put it where x is. So I'm going to then have this. And that's starting to look a little more like y equals mx plus b. Since ultimately we're trying to graph a linear graph, we want to graph something of the form y equals mx plus b. And we're going to get that if we line it up next to our equation. And this tells me that if I put 1 over I on my y-axis. And if I put R on my x-axis, I should get something linear. The slope of that line ought to be 1 over the battery's EMF, 9.49 volts in this case. And the intercept ought to be R over the EMF. So in terms of what I want, I'm actually interested in the intercept in this case. So ultimately, I'm going to make this graph, and that's what's going to get me the things I want. The slope ought to be 1 divided by the voltage. That'll be a nice check. The intercept will allow me to solve for little r. Once I get the intercept, I'll just set it equal to little r over the battery's EMF and solve for little r. And here's the thing. If this is linear, my model has checked out. If it's not linear, then there was a problem with the model I came up with, and maybe there's something about my circuit I didn't know. So we never just do one calculation when we collect lots of data. We collect a range of an independent and dependent variable. We come up with a model. We manipulate the equation using algebra so that it looks like y equals mx plus b. And then we better get a line. If we don't, something's wrong. So let's look at a couple other examples of linearization that you might have seen in previous courses. So earlier this year, we studied the Bernoulli equation, and we found that for water that falls out of a bottle at a certain distance below a surface, we found out that it reduces to a potential energy term equals a kinetic energy term. And we end up with V equals the square root of 2GH. And if we had a bunch of measurements of how fast water was going and how high it was, we can think of this as a dependent variable and height as an independent variable. So what we did earlier in the year is we graphed lots of different heights and figured out how fast it was going. So this is how we linearized in that situation. I squared both sides, so I had V squared equals 2GH. I put V squared on the y-axis. I put H on the x-axis. And that meant that my slope ought to be 2G. In a class where you've studied simple harmonic motion previously, this is the equation for the period or the time it takes for a back and forth on a pendulum. So a common lab would be to have lots of different length ropes and measure the time for a back and forth. And you can see by linearizing this, and you could do it in either of these two ways, the slope term has G in it. So this actually ends up being a really good measurement of G. I have students in classes like this plot period squared versus length of the pendulum, and we get really close to 9.8 as a measured value of G. I've had some classes do Newton's second law this way. I have them collect data on acceleration versus mass as they have an object sitting on a table, maybe on wheels, and another hanging weight that pulls it down. We expect acceleration to be sigma f over m, and that means an inverse relationship with mass. So if you put 1 over m on the x-axis and a on the y-axis, that should give you a line. So getting used to this idea that you take some fundamental physics equation and line it up next to y equals mx plus b is really important. Anytime you're given multiple values of data, typically what you're supposed to do with it is linearize something and use the slope and or the intercept to find a value. A lot of times on tests, you'll be given random blank columns along with your data. And that's what I've done on this worksheet. What we would do here is we would ultimately be trying to find 1 over current, as that's what we were told to graph on our y-axis. And probably I would have you convert these to amps first. We wouldn't use this column at all because we don't have to manipulate resistance at all. So if you see a table on a test and it's got a bunch of empty columns, know that they're there for you if you need them as you manipulate an equation like this. I hope that helped with linearization. Please check in with me if you need any more help with it. Thank you.